So welcome to part 3 of lecture 12. So we've been talking about invertible maps, and I wanted to show you an example of something that's not an inverse. So this may actually help you with your understanding. So here I have my vector spaces, PTR, all the polynomials of degree 2 or less, and I'm going to map to all the polynomials degree 1 or less. And I'm going to take a linear map D just to be the differential function, i.e. it takes a polynomial and maps it to its derivative. Okay, so this is a linear map. We've seen this in a previous lecture. And we're going to look at what you might think would be the inverse, which would be kind of the integration property. So we're going to look at a linear map from P1R to P2R, and it's defined by taking a polynomial degree 1, and we map it to B0x plus B1x squared over 2. So here we have two functions, and it kind of looks like that they're inverses of each other, but they're not. And I wanted to kind of show you explicitly why they're not inverses of each other. So the reason is, in one direction, it does look like we have the identity operator. Okay, so let's say I first take the derivative of something of degree 2. So I first take I first take the derivative and then I integrate. Right? So when I take the derivative, I get a1 plus a2x, and then when I integrate, I get a1x plus a2x squared. Oops, I get a2x squared. And then if I do it in the reverse order, if I first integrate and then take the derivative, so I'm first going to integrate, so I get b0x plus b1x squared over 2, and then I take the derivative, I get b0 b1x. So when I look at this, what I notice is that in the second statement, no matter what I start with, I get the same thing at the end, right? So I get that d composed with integration, right? First do integration and then take the derivative is the same thing as the identity operator on P1R, but it doesn't work in the reverse direction, okay? So when you integrate, if you first take the derivative and then you integrate, you don't get the identity function on PTR. Right? Because what happens is when you take the derivative, you lose the constant information, and when you integrate it, you don't see it back anymore. So you get something that does not behave like the identity function. So it looks like in one direction we had the identity we get the identity, but we don't have it for both. So it fails to be It fails to be an inverse. Okay. So one of the words that was in the title was the word of isomorphism, and now I just want to spend some time talking about what it means for what does that term mean. So an invertible linear map is called an isomorphism, and if there's an isomorphism, we say that two vector spaces V and W are isomorphic. Okay, if there's an isomorphism between the two. And one way to think about what it means is that V and W are isomorphic. What that means that V and W are the same vector space, but with different labels. Okay, so when we say two vector spaces are isomorphic, it really means that there's not really any difference between these vector spaces. The only difference is in the way in which we wish to express them. Okay, so kind of an example of this is to think about the vector space of R2, so all two tuples, and the vector space of all polynomials of degree 1 or less. And we can define a linear map from R2 to this set of polynomials by taking a pair AB and mapping it to A plus BX. And you can convince yourself that this is an isomorphism. This is an isomorphism. And probably the easiest way to check is to use the previous theorem to show that it's both surjective and that it's injective. So these two vector spaces R2 and P1R are really the same vector space. The difference is how we're expressing it. Here we're using tuples, and here we're using polynomials. So in the next part, I'm going to give you a very useful theorem which allows us to quickly decide if two vector spaces are isomorphic.